Welcome, everyone. You're in the Case History session. My name is John Allen with Owens Corning, and I, along with my co-chair, Kush Cohen of Macmillan Jacobs, will be your session chairs for the next hour. We have three exciting presentations today over a wide range of geosynthetic topics.
A couple of things to note before we start the presentations. You'll have the opportunity to ask questions during this on-demand session by clicking the questions button at the bottom of the video window. Your question will be sent to the presenter to answer as soon as they are able. To claim PDH credits for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you fill out a survey for any sessions that you have attended. And please note that you will need to include a verification code shown in the session to verify that you did attend the session and ensure that you received the proper credits. Please enjoy the presentations.
Hello everyone and welcome to this presentation. My name is Mariana Ferrara and today I will be presenting reinforcement over soft soils with high-strength geogrids and some case studies. Construction over weak foundation soils is generally associated with poor bearing capacity and excessive differential settlements. The presence of poor ground conditions is challenging and it is the most frequent cause of long construction durations. Several alternatives can be employed to deal with this problem, like bypassing the poor ground through relocation of the project, removing and replacing the soft soil, designing the plant structure to accommodate the poor marginal ground, or modifying the existing soils with different techniques. Usually, the function of these alternatives is to increase the shear strength and the bearing capacity, but also increase the density and the drainage and provide lateral stability. Typical ground improvement techniques include vertical drains, lightweight fills, deep compaction, aggregate columns, column supportment embankments, reinforced soil structures, grouting, soil mixing. Each one of these techniques has limitations, mainly due to long construction time and high costs. An alternative solution that can help with these two aspects is the use of geosynthetics. Construction of embankments over weak foundation soils with geosynthetic is also known as basal reinforcement. It is an application where a high-strength geosynthetic reinforcement is placed directly on top of the weak foundation, and then the embankment or the structure can be built on top of it. We can identify three different types of basal reinforcement: over weak foundation, over columns, or over voids. And today I'm going to be focusing on the first two. So, basal reinforcement alone or in combination with vertical drains to control the stability of the structure without controlling the overall settlement, and basal reinforcement with foundation stabilization such as rigid intrusions to prevent or limit settlements. In the first case, the geosynthetic, it's going to help with the bearing capacity, with increasing the bearing capacity of the foundation. In the second case, the geosynthetic reinforcement is going to help creating kind of a bridge across the columns to distribute the load of the embankment and optimize the column design itself. And now some consideration about the first basal reinforcement, so the one over weak soils. The stability of the embankment is mainly governed by the shearing resistance and the construction of the embankment itself by the bearing capacity. So the stability of the embankment is most critical during construction and right after it, when consolidation of the soft foundation soil has not yet occurred. A geosynthetic reinforcement can be placed at the foundation level of the embankment to prevent the shear failure of the embankment and of the foundation soil. The design approach for the basal reinforcement over soft soil is to verify the potential mode of failure of these limit states that are in this slide. So the local stability, the rotational stability, the lateral sliding of the embankment, the foundation extrusion, and the overall stability of the system itself. Although a geosynthetic reinforcement may change the stress distribution, leading to a possible reduction in differential settlements, total foundation settlements is not directly affected by a geosynthetic reinforcement layer. One form of basal reinforcement over weak foundations is called reinforced granular mattress. It is a three-dimensional structure formed from a series of interlocking units fabricated directly on top of the soft soil from geogrid reinforcement and filled with granular material. The RGM interacts with embankment because it creates an adhesive interface between soft foundation and granular mattress, but also a stiff platform to ensure an even distribution of loads onto the foundation and a more uniform stress field within the soft foundation. These properties enable the RGM to influence the deformation of the foundation soil and may be used to mobilize the maximum shear strength and the bearing capacity. A reinforced granular mattress solution was used for the case study I'm about to present. The port of Guaymas, located on the northwest coast of Mexico, is one of the most important ports in Mexico from both commercial and touristic point of view. It manages the shipment of agricultural and mineral bulk, but also general cargo. It is an important hub for commercial relations between Mexico and the southern part of US, moving up to 3 million tons of mineral like copper and steel. The development of the port took place through subsequent stages of land reclamation from the sea, causing the foundation soil to be saturated and very soft. In fact, the geotechnical investigation showed a 46 feet deep layer of soft soil characterized by gray-green silty sands and dark brown sandy clays with high plasticity. In recent years, the port storage area has been experiencing significant settlements due to the increase of loads managed in this area and poor condition of the foundation soil. So the Port Authority of the Port of Guaymas decided on a major renovation of the area, of the storage area, to build new concrete pavement and a warehouse. As I said before, a reinforced granular mattress with high strength geogrids was selected as a solution for this project. The Port Authority chose it because of its advantages compared to traditional ground modification techniques. It is easy and fast to install, and it's more cost effective. The total tensile strength of geogrids required to support the load of the granular material itself and the overload of the minerals dumped in the storage area of the port for a total uniform load of more than 9,000 pounds per square foot was calculated using the design method for embankments over weak foundations included in the British Standard BS 8006-2010. This method considers both short and long-term tensile strength of the geogrid. So the resulting ultimate tensile strength already considers all the reduction factors for tensile creep, installation damage, and environmental degradation. Moreover, the design of the geogrid reinforcement was carried out using the elastic multilayer analysis. So given the thickness of the mattress and considering separately the effect of the static load and the instant effect of dynamic loads, it is possible to calculate the distribution of the horizontal forces in the whole mattress structure and select the appropriate geogrid for each layer. The geogrid used in this project was a high-strength uniaxial geogrid characterized by a high-tenacity polyester core with a low linear density polyethylene coating. This coating is resistant to physical, chemical, and biological conditions found in reinforced soil structures. The reinforced granular mattress layout consisted of a 3.28 feet thick aggregate layer with two sets of transversally installed high-strength uniaxial geogrids. The construction of the reinforced granular mattress included the following steps, starting from picture number 1, preparation of the site by excavating a few inches of the entire area and cleaning it from sharp objects. Picture number 2, placement of the first layer of high-strength geogrid. The rolls were placed on the west side of the storage area with the use of a lifting beam and unrolled towards the east side, ensuring that no slack or undulations occurred. At both edges of the geogrid, an anchorage length of 6.5 feet were left out to eventually wrap around the geogrid. Picture number 3, we see the installation of the second layer of high-strength geogrid and the placement of fill material. The fill material was placed into lift, paying a lot of attention during the spreading and compacting phases. It has to be spreaded and compacted in the longitudinal direction of the top high-strength geogrid. Picture number 4 shows the second set of geogrids, so the repetition of steps number 2 and 3. And picture number 5 shows the storage area at the end with the concrete pavement and the foundations for the warehouse. The second basal reinforcement I'm presenting today, it's the one over piles. So in this case, it's a combination between rigid intrusions, such as piles or columns, and a geosynthetic reinforcement. This type of solution has a lot of applications, such as embankment stabilization, roadway widening, retaining wall foundation support, etc. The two elements have different functions. The columns or piles provide support and settlement control by transferring the load through the soft foundation into a stiffer foundation, while the geosynthetic reinforcement distributes the load of the embankment on top of the piles. Because the most critical aspect when designing a column-supported embankment is that the load must be transferred effectively to the columns to prevent punching of the columns into the soil structure and avoid severe differential settlements in the surface of the structure. So the spacing in between the piles is very crucial during the design of this type of solution. A load transfer platform is commonly used immediately above the columns to help transfer the load from the embankment to the columns. As per the Federal Highway definition, there are 3 different types of load transfer platform. One is the reinforced concrete structural mat, and the other 2 consist of select granular fill with 1 or more layers of geosynthetic. The goal of the geosynthetic reinforcement here is to span across pile caps carrying all or a portion of the load coming from the embankment into the columns. And by doing so, spacing between piles can be significantly increased and pile cap sizes can be decreased. Always following the definition of the Federal Highway, there are 2 main approaches to geosynthetic reinforced load transfer platform. One is the beam method and the other one is the catenary method. The beam method is the most known and used and considers multiple layers, minimum 3, of a low-strength geosynthetic reinforcement such as a biaxial geogrid, spaced within a select granular structural field that act as a single rigid beam. While the catenary method, based on the British Standard 8006-2010, considers only one layer of high-strength geosynthetic that act as a catenary single layer at the interface between the columns and the embankment. In this case, the geosynthetic reinforcement used is a uniaxial geogrid made of polyester yarns with a low linear density polyethylene coating. The maximum tensile strength that this uniaxial geogrid can reach is 100,000 pounds per foot. The catenary method was used to calculate the tensile strength of a geogrid for a load transfer platform in the I-95 Telegraph Road Interchange project. In early 2018, extensive upgrades to the interchange began as a part of a multi-year project tied to the final phase of the Woodrow Wilson Bridge project. The goal of the new interchange was to improve vehicle capacity and provide safer and more efficient travel through a series of bridges and ramps. The project was the single largest design, bid, and build construction contract ever awarded by the Virginia DOT. This massive interchange project included column-supported embankment with aggregate piers and a load transfer platform with geosynthetic reinforcement. Virginia DOT specifically requested high-strength geosynthetic reinforcement, and an ultimate tensile strength of 38,000 pounds per foot was calculated using the catenary method. Uniaxial geogrid installed in 2 different layers was used for basal reinforcement over aggregate piers and under a mechanically stabilized wall. Also in this case, the construction of the load transfer platform went through different steps. Starting from the preparation of the site by cleaning from sharp objects the entire area and placing the 2 layers of geogrid on top of the aggregate piers, followed by the placement of the fill material in different lifts to create the embankment on top of the basal reinforcement. Thank you all very much for attending this presentation. It was a pleasure for me sharing this information with all of you. Please feel free to ask any question, or if you need additional information, just reach out to me through my email address. Stay safe. Thank you. Bye.
Hi, everyone. Thanks for tuning in. My name is Chase. I'm a water resources engineer at a company called NGO Incorporated. We're a mid-sized earth sciences consulting firm based out of the San Francisco Bay Area in California. And today I'm going to be presenting a case study that my colleague Joseph Tootle and I worked on. It's called Water-Filled Barrier Walls for Stormwater and Sediment Control on Steep Slopes. To start with a bit of background, the case study took place at a hillside grading construction project in Northern California, and the contractor needed to work throughout the rainy winter season in order to meet the construction schedule demands. So this involved clearing and grubbing a 10-acre hillside right before the rainy season with predominantly silty sand, soils, and slope grades steeper than 2 to 1 in many locations. So this created an erosion control and stormwater management challenge. For context, construction stormwater in California is regulated by the Construction General Permit, often called the CGP, and it requires that best management practices, known as BMPs, be installed year-round on construction sites, and it also limits stormwater discharges during rain events to a turbidity value of less than 250 NTU. And for anyone who's seen a vial of water that's around 250 NTU, it's actually somewhat clear. So this is a pretty strict discharge standard. And because the contractor was going to be grading during the rainy season, it didn't make sense to use more traditional slope BMPs such as hydroseed, straw wattle, and geotextile blankets and nettings, because the contractor would need to install those before every storm and then uninstall them following the storm in order to continue their grading operation. So because of that, we decided to try out a more non-traditional barrier wall BMP to help prevent stormwater from leaving the site. The product we used is called Muscle Wall. It's a portable water-filled barrier wall that comes in a variety of heights. We went with the 4-foot tall model, and each segment of the barrier wall is about 6 feet long. And those segments weigh 120 pounds when they're not filled with water and about 1,400 pounds when filled. So how does the product work? Step 1, the barrier walls are slid into place to create the desired configuration. Step 2, the walls are filled with water, generally using a water truck. Step 3, each segment is secured to the adjacent segment using ratchet tie-down straps. Step 4, the barrier wall alignment is wrapped with a geotextile liner, often a filter fabric or a thick plastic product. Step 5, gravel bags are placed at the toe of the barrier wall to prevent underseepage. And then step 6, the metal clips are installed on top of the wall to secure the geotextile liner to the wall itself. For some examples of the product in use, you can see here it's being used for flood control. Here it's being used for sediment control. And here for liquid containment. For our site, the strategy was to install a series of these barrier walls along the steep hillside to act as check dams to reduce the velocity of stormwater coming down the slope, and to also act as basins. We knew that if stormwater was to leave the site, it would exceed the turbidity threshold, so we wanted to make sure we were detaining as much stormwater as possible. So overall, the system consisted of 9 of these barrier wall basins. On the upslope end, you can see is MW8 and MW9, and on the downslope end, we have MW1 and NW2. And the system was designed to detain about 2 inches of rain over 6 hours. And for storms that were forecasted to exceed this volume, we staged a series of water trucks at the furthest downslope basin where water could be pumped into and then transported to a large infiltration basin in a flat region of the site. To implement our placement strategy, the contractor ordered about 4,000 linear feet of the barrier wall product, and it was delivered on 7 truck trailers in total. And just for stockpiling context, each pallet that the product came on came with 12 walls, 6 stacked on top of the other, and that took up about an 8-foot by 6-foot footprint. When it came to deployment, if the barrier wall basin was to be placed on soil, the contractor would often do some minor grading to create an even surface for that barrier wall to sit on top of. If the surface type was either asphalt or concrete, obviously grading was not needed in that situation. So the contractor estimated that to install 500 linear feet of the barrier wall, it took about 9 hours if grading was needed to create an even surface, and about 5 hours if grading was not needed. This table summarizes some characteristics of the deployed basins. As you can see, the lengths range from 80 feet to 500 feet. The cross slopes range from flat or 0% to upwards of 20%. And the surface placement types vary from concrete to asphalt to compacted soil. And each barrier wall, as part of these barrier wall basins, was filled completely with water to increase the stability, except for barrier walls that were located directly over active haul roads. Those wall pieces were left empty so that the contractor could easily move them out of the way in case that haul road needed to be accessed. This slide shows an aerial view of the deployed basins. As you can see on the left side, some of those basins are placed on that asphalt road, and more in the middle and upslope, those basins are placed on compacted soil. Moving on to our findings, I'm going to briefly discuss each of the 9 barrier wall basins' performance during storm events. And luckily, during our case study period, we received an above average amount of rainfall. So it gave us a decent amount of opportunities to really evaluate our BMP barrier wall strategy. Starting with MW1, on the left-hand side, you can see the initial configuration. The basin is placed on a concrete sidewalk with a cross slope of 10%. And as you can see on the right-hand side, it was successful at detaining large volumes of sediment following storms, which the contractor would then excavate out to create more capacity before each rain event. Basin MW2 had 4 unfilled barrier wall pieces, as shown in red, and those were anchored by 3 water-filled barrier wall pieces on either end, as shown in blue. The reason for leaving those middle barrier wall pieces empty was so that the contractor could more easily remove those barrier wall pieces during dry weather so that the haul road could be used, as shown in the example below. During the first major storm, the barrier slid out of place due to sediment buildup and impact. To prevent sliding from occurring during future storms, we added 2 additional water-filled anchor pieces on each side of the basin. Following this revised configuration, the basin did not slide during subsequent storm events and detained turbid stormwater. Basin MW3 was similar to that of MW2 in that they both had empty barrier wall pieces across the haul road. During the first major storm, the barrier wall pieces disconnected from each other and slid out of place due to sediment impact and buildup. However, with the addition of 2 additional water-filled anchoring pieces on each tail of the basin remained stable and held back turbid stormwater during subsequent storm events. Next, we'll move on to Basin MW4, which was located in the lower middle portion of the hillside. Unlike the other basins, MW4 was placed at the top hinge point of an already excavated sediment basin, so this added an extra 4 feet of height to that existing 3 feet deep sediment basin. In addition, the plastic liner was wrapped around the top of the barrier wall and then continued down that excavated basin's side slope to help prevent seepage under the toe of the barrier wall. Here you can see an overview of the combined barrier wall and excavated sediment basin. On the left, you can see the empty basin before a storm, and then on the right side, you can see the basin filled to the brim with turbid stormwater following a storm. And this is where we'd often have water trucks staged during storm events to pump water into when this basin got close to overtopping. Next, we'll look at Basin MW5, which is located just above MW4 in the upper middle portion of the hillside. Basin MW5 was the longest of the 9 barrier wall basins. In the photo below, you can see an image of it prior to a storm event, and then here's what it looked like filled to capacity following a storm event. While this basin didn't experience any stability issues, even when filled to capacity with 4 feet of sediment and water, it did experience some seepage under the toe of the barrier wall, and this was due to the plastic liner not continuing along the inside of the barrier wall basin, and also due to small irregularities in the ground surface, which created gaps for water to flow through. Next, we'll look at Basin MW6, which is located behind those trees in the upper left-hand corner of this aerial. Similar to Basins MW2 and 3, Basin MW6 was placed across a steep asphalt road. However, unlike Basin MW2 and 3, Basin MW6 didn't utilize any 90-degree corner pieces, as you can see by its semicircular shape. During the same storm where Basins MW2 and 3 had stability issues, Basin MW6 remained stable and held back 4 feet of sediment. Similar to MW6, Basin MW7 was placed across a steep asphalt road and had empty barrier pieces in the middle. However, unlike MW6, it also had 2 90-degree corner wall pieces. During the first major storm, the barrier wall basin as a whole did not slide. However, the individual barrier wall pieces that were not filled with water rotated outward. Since this area of the job site did not need to be accessed as frequently, the revised configuration for Basin MW7 consisted of filling up each barrier wall with water. During subsequent storms, the basin remained stable using this configuration. Basin MW8 was located in a relatively flat upper portion of the hillside, so it didn't receive a ton of runoff. Below you can see a picture of it before a storm, and then after a storm. As you can see, it's not having any trouble detaining that turbid stormwater, but it didn't receive nearly the volume of sediment and stormwater as the downslope basins. Finally, we'll take a look at Basin MW9, which is located in the upper right-hand corner of this aerial. Similar to MW7, Basin MW9 had 5 empty barrier walls in the middle and also used 2 90-degree corner wall pieces. However, unlike MW7, Basin MW9 was placed on compacted soil instead of asphalt. Here's a picture of the basin filled to capacity during a storm event. This basin would often overtop with water during storm events. However, throughout the case study period, it remained stable and experienced minimal underseepage. And here you can see it detained about 3 feet of sediment following a storm event. Overall, the system of barrier wall BMPs was an effective strategy for detaining large volumes of sediment and turbid stormwater along the hillside, and it also allowed the contractor to continue grading operations throughout the rainy season. Of the 9 barrier wall basins, 6 were stable throughout the entire case study period. Once the 3 basins that initially had stability issues were reconfigured and properly anchored, they were stable for the remainder of the case study. The 3 basins that initially had stability issues had 4 things in common. 1, they had cross slopes greater than or equal to 10%. 2, they were placed on asphalt. 3, they had empty barrier walls. And 4, they utilized corner wall pieces. While basin MW6 was on a slope greater than 10%, placed on asphalt, and contained empty barrier walls, it didn't experience any stability issues throughout the study period. And this was likely because of its more stable semicircular configuration. It didn't utilize any of the 90-degree corner wall pieces. In general, stress tends to concentrate over sharp changes in geometry. And it was also observed that for some of the other basins where barrier walls had come out of place or rotated, it was a corner wall that was the weak point. While basin MW8 was placed on asphalt, contained empty barrier walls, and also utilized those 90-degree corner wall pieces, it didn't experience any stability issues. And this is likely because the basin was located on a 5% slope as compared to that 10% or greater threshold we were discussing earlier. And the basin also never filled to capacity due to its upslope location on the hillside. While basin MW9 was placed on a slope with an approximately 10% grade, contained empty barrier walls, and also utilized corner walls, it didn't experience any stability issues. And it appears the compacted soil that it was placed on top of was likely the reason for its increased stability. This is because the coefficient of friction between the barrier wall pieces and the soil is generally higher than that of the barrier wall and asphalt. In addition, the barrier walls were able to settle into the soil as opposed to sitting directly on top of relatively rigid asphalt. From the case study, we found that sliding is likely to be the most common failure method if the barrier walls are not properly anchored on steep slopes, so we performed a retaining wall analysis to calculate the sliding factor of safety for varying slope grades. As you can see from our results, the sliding factor of safety decreases with increasing slope grade, is greater for soil compared to asphalt, and approaches 1 at a slope grade of 10%, which aligns with our field observations. To increase stability, additional water-filled barrier walls, or K-rail, can be placed perpendicular to the alignment, as shown here. For horseshoe-shaped basins, additional water-filled anchor walls can be placed on each end, and if enough anchor walls are used, some barrier wall pieces in the middle of the basin can even be left unfilled. Based on our case study, we created this table with recommended rule of thumb ratios of water-filled to unfilled barrier walls to improve basin stability for various slope grades. We found that leaving some barrier walls unfilled allowed for continued use of haul roads during non-storm conditions, and then if a storm was forecasted, the contractor could quickly reconnect the unfilled barrier walls. To reduce seepage under the barrier walls, strategies shown on this slide could be used. To reduce uncontrolled overtopping of the barrier walls, the system could be equipped with a discharge port, as shown here. A hose could then be connected to the discharge port and routed to an active treatment system or other water quality BMP. We found the barrier wall product to be an effective alternative to traditional barrier BMPs such as sandbags and K-rail. For comparison, one 4-foot tall barrier wall is equivalent to 470 sandbags. In addition, the Army Corps of Engineers found the barrier wall product was 25 times quicker to construct and experienced 4 times less seepage compared to sandbags. Compared to K-rail, we found the barrier wall product to be easier and also greener to deploy because it did not require the use of heavy machinery. The barrier walls can be lifted and put into place by hand and then filled with water. To conclude, the use of water-filled barrier walls for stormwater and sediment control on steep slopes was a largely effective BMP strategy for the hillside construction project. The series of 9 barrier wall basins held back large volumes of turbid stormwater and eroded sediment, and also reduced the velocity of stormwater as it made its way down the hillside. When properly anchored, the basins remained stable on slopes of varying steepness and surface type. Since the end of the case study period, we've reused the barrier wall product at the project site for a variety of other applications, including as a perimeter control BMP, as a temporary retaining wall during geotechnical construction activities, and as a diversion channel to route stormwater away from a sensitive area of the construction site. Thanks for tuning into this presentation. If you're interested in learning more, the case study paper goes into more depth on everything that I discussed here, and definitely feel free to reach out to me if you have any questions or comments.
Hello, my name is Brian Fraser. I'm a Vice President at Layfield Geosynthetics, and on behalf of the IFAI and Geosynthetics 2021, I'm very pleased to be presenting today on the economics of geosynthetic floating covers and reservoirs. Open reservoirs have been used for thousands of years and date back as far as 3000 BC, where they were used for drinking water and irrigation purposes. And today they're still commonly used, however, typically incorporate a geosynthetic floating cover system. And this picture shows the Ramona Water District and Reservoir. It uses a tension cable floating cover system which was installed in 2020. And there's various methods and systems used today to store large quantities of potable water or irrigation water. These include above ground steel or concrete tanks, steel or concrete towers, underground concrete clear wells, and open-top reservoirs with geosynthetic floating covers. Geosynthetic floating covers and open-top reservoirs are known to be one of the most economical methods of storing large quantities of water. They're used commonly in both concrete and earth-constructed reservoirs, and they're designed to eliminate water loss due to evaporation. They prevent dirt and debris from contaminating the water source, and they help to control the amount and cost of disinfectant used in water treatment. So let's look at the economics of floating covers and reservoirs. This is the Upper Chiquita Reservoir, owned by Santa Margarita Water District in California. It's an 18-acre, 244 million gallon reservoir for potable water storage. It was completed in 2009 after 1.5 years of construction time. And it incorporates a 60 mil CSPE or chlorosulfonated polyethylene 3-ply defined sump floating cover. The overall construction cost was $53 million, and that included all of the engineering, earthworks, mechanical, and the installation of a liner and cover. That works out to the average construction cost and price of 22 cents per gallon of water. And in comparison, this is the Kelly Butte Clearwell Reservoir, owned by the City of Portland in Oregon. It's a 25 million gallon or 95 million liter concrete underground clearwell potable water storage. It was completed in 2016 after 4 years of construction and included 16,000 cubic yards of concrete. The total overall construction cost was estimated at $90 million US, working out to the average price per gallon of $3.60 US. And that's $3.48 more than the Upper Chiquita Reservoir and floating cover system. So let's look at the economics of floating covers and reservoirs for water savings. This is the West Texas Evaporation Control Cover Project. It was located in the Permian Basin in West Texas. It was part of upstream oil and gas hydraulic fracturing. And the water costs were quite high in this region, averaging 50 cents to $1 per gallon. The region is known to be very hot, arid, and windy. And evaporation rates can reach as much as 90 inches or 2.3 meters annually. With an earth-constructed reservoir, approximately 250,000 square feet, or 23,234 square meters, and we actually installed 8 covers in this region. The total cost for the supply and installation of the floating cover was $325,000, and that was for a 40 mil or 1 millimeter polyolefin alloy floating cover. The annual evaporation losses calculated by the owner were $310,000 US. So that works out to a return on investment in terms of time of 13 months. CSPE, or chlorosulfonated polyethylene, is recognized as the leading material for floating covers in municipal water applications. CSP in potable water commonly performs for over 30 years. And there's been numerous materials introduced and used over the past 25 years for floating covers, including reinforced polypropylene, reinforced polyethylene, linear low-density polyethylenes, HDPE, PVC, and various EIA alloys. And our company has experience supplying and installing most of these materials. And there's been varying degrees of performance success with the different materials, lasting typically anywhere between 5 and 20 years. And the typical failure mode has been UV degradation, premature stress cracking, leaking, or loss of mechanical properties. The requirements for a good floating cover material include long-term UV resistance, chemical resistance to chlorine and different disinfectants, very good flexibility and fatigue properties, and overall very good thermal properties, both high and low temperatures. CSPE as a geomembrane was first introduced in the mid-1970s for floating covers and liners in Southern California for municipal applications and the southwest region of the United States in mining applications. It's a synthetic rubber-based material manufactured by the calendering process. It's produced as a thermoplastic, however, over time cross-links or vulcanizes into a thermal set. And it's noted for its excellent abrasion, flexibility, chemical resistance, thermal properties, ability to be repaired, and outstanding UV properties. It's defined as a flexible membrane liner designed for prefabrication and flexibility. And it's become noted over the last 40 to 45 years in municipal water applications, and its excellent resistance to different types of disinfectants, including chlorines and chloramines. It's NSF 61 tested and certified to be used for public drinking water applications in North America. And it can be produced into just about any color. It also comes with an industry-leading 30-year weathering warranty. This project profile is known as the Upper Stone Canyon. It's owned by Los Angeles Department of Water and Power. It's their Upper Stone Canyon Reservoir, located just outside of Beverly Hills, California, and was installed in 2019. It had a total capacity of 139 million gallons, or 526 million liters. It incorporated a 700,000 square foot, 45 mil 3-ply CSPE floating cover system in a defined sump construction, and it was for potable water storage and treatment. Initially, the owner considered a concrete clear well. However, the total cost was $140 million US and would take 4 to 5 years of construction time. As a result, they went with a concrete open-top reservoir and floating cover system. The total cost was $35 million and took 1.5 years to complete. The floating cover has an estimated service life of over 30 years and is designed to be replaced at that time. And the owner required a special aqua green color for the floating cover to tie into the environmental requirements in the region. This project profile is the Hinkle Reservoir, and I initially talked about the same project in a paper at Geosynthetic 2019 in Houston, Texas. It's owned by San Juan Water District in Granite Bay, California, just outside of Sacramento. It's a 62 million gallon or 238 million liter capacity reservoir. It has a 550,000 square foot CSPE defined sump floating cover system for potable water storage. And it was installed early in 1980 and is currently 41 years of age and still in application. And at the 37-year mark, our company did some minor surface repair work on the same cover. The owner chose an open-top reservoir and cover system based on the economics, and at the time reported that the floating cover option was 35% the cost of an above-ground steel tank system. And today, at 41 years of age, to our knowledge, it's the oldest known floating cover still in operation, and it's scheduled to be replaced sometime in 2021. And it's another very good example of just how well CSPE performs and weathers in a floating cover application. This picture shows a CSPE defined sump floating cover system in Southern California that was installed in 2008. The reservoir is actually filled and the cover is in application. And you can see how well the floats and sumps are working to keep the cover nicely tensioned, no wrinkles, allowing it to follow the freeboard, as well as allowing personnel to walk on the cover when required to perform any maintenance or operations. And this picture shows our construction crews installing surface floats and the sump system as part of a recent CSPE project installed in Pittsburgh, Pennsylvania. And this slide shows a perimeter tension cable CSPE floating cover system that was installed on the USA-Mexico border. The original cover was installed in 1988 and replaced in 2018 after 30 years. And the picture on the right actually shows the tensioning towers and cables pulling a reinforced edge, keeping the cover nicely tensioned in application. I'd like to acknowledge 3 individuals who have played a key role pioneering and developing operational performance improvements in floating covers over the many years. These include Mike Neal. Mike is a senior project manager at Layfield USA, based out of Eugene, Oregon. And over the past 30 years, Mike has project managed many floating covers around the world. Also like to acknowledge Doug Hiltz from Hiltz Consulting Group out of Chino Hills, California. Doug is an industry-leading designer and floating cover expert and has played a key role improving the designs and performance of floating covers over the years. And Mr. Paul Vince. Paul Vince is a principal materials engineer at Aurocon in Adelaide, South Australia. Paul is a material corrosion expert and has tested various geosynthetic materials used in floating covers. Paul has also written numerous papers on geosynthetic materials in floating covers and is a noted expert within the field and in Australia. On behalf of the IFAI and Geosynthetics 2021, I'd like to thank you for the opportunity to present today on the economics of floating covers and reservoirs. My name is Brian Fraser. I'm the Vice President of Layfield Geosynthetics, and I can certainly answer any questions on this paper. You can reach me at brian.fraser@layfieldgroup.com. Thank you for the opportunity to present.